Well, hello again, everybody. I think it's time that we talk a little bit more about what happens to electrical charges. There's one right there. It's yellow, so obviously that's a positive charge. Just kidding. But let's suppose that that is a positive charge. Let's say of 5 times 10 to the negative eighth power coulombs. Now remember, that's a very small amount of charge in terms of coulombs, but that's a whole bunch of positive charges, of excess positive charges. Let's suppose furthermore that we put a little monitor of some kind on this charge and notice that it's experiencing a force of 2/1000ths of a Newton, and that force is pulling it or pushing it to the left. Question for you. What's causing that to happen? Why does the charge experience the force? Well, there are a couple of possible answers. One of them might be maybe there's another positive charge right there that's causing a force in that direction because, two positive charges are going to repel each other. And furthermore, there's a second, or maybe third in this case, positive charge right there that's causing a force in that direction. And maybe the vertical components of those two forces cancel each other out, but the horizontal components add, and so you end up with the force that's shown there. That's one possibility. Or maybe there's a whole lineup of charges down here, maybe smaller ones, where the vertical components all cancel, but the positive ones add up to give us this. So that's one possibility. But there's another. Let's suppose that there's a negative charge, green for negative charges, I guess, sitting right there. That would pull our original positive charge to the left. So it would experience, once again, that same amount of force, assuming the green charge is the right size and the right distance away. In other words, we know that there's a force, but we don't know necessarily the configuration of the charges that are causing that force. And they may never be known. In that situation, we need to be able to describe what's going on with something called an electric field. An electric field describes what happens to charges, not necessarily what causes it to happen to charges. Okay? A couple of properties of electric fields that you need to be aware of. First, it's asking the question, whoop, went a little too fast there. It's asking the question, what will a positive test charge do? A negative test charge will go in the opposite direction, okay? Because, for example, if something's pushing a positive charge to the left, that means it'll pull a negative charge to the right. That makes sense? Second thing, we already hinted at this, you can draw an electric field with lines and arrows. However, there are some important properties about those field lines when you draw them. They begin at a positive charge or at infinity, whatever at infinity means. They end on a negative charge or at infinity. The number of lines that you see in a given region of space is proportional to the strength of the electric field. That is, how hard it'll push a positive charge or pull a negative charge. And finally, the lines of an electric field do not cross. Now you might be wondering, why should the lines not cross? Well, maybe it's for this reason. Maybe if the lines cross, all the atoms in the universe will explode at the speed of light. No, that's if the streams cross. No, it's for an entirely different reason. It has to do with this idea. Let's suppose we have a line here and another field line right here, indicating that a positive charge will try to go in both directions. Well, that doesn't make any sense. What would actually happen is this. The field lines are a vector. We add vectors arrowhead to endpoint, and so what the positive charge would actually do is go in this direction. And so we can replace these two lines with one line, and so anytime field lines intersect, you can just replace them with a single line. This is, for example, what they might look like. Around a positive charge, the field lines are spreading outward, and around a negative charge, the field lines are pointing inward. Why? Again, think what would happen. If I put a positive test charge right here, it's going to be repelled by this, and so it's going to show what would happen to a positive test charge. If I put a positive test charge here, well, the field is showing that it's going to move this way, and sure enough, that's because the negative charge is going to attract it. Notice also that the field lines are denser when you're closer to the charge. That is, they're closer together. If I take this same circle and redraw it out here, it might only include one of those field lines. And so that means the field is stronger when you're closer to the charge, which we know is true from Coulomb's law. So that's the basic idea of a very simple electric field. These two charges happen to have the same strength because they have the same number of field lines around them. Okay, so there would be the same amount of charge, except of course with opposite signs. If we try to draw the field of two equal charges that are near each other, we get something that's a little bit more complicated. Here's the idea behind it. Let's suppose, for example, that we put a positive test charge right here. Okay? This charge will repel the charge this way. This charge down here, the negative, will attract our positive test charge this way. When we add together those two force vectors, we get a horizontal force vector right there. On the other hand, if I, let's say, put my positive test charge here, okay, positive test charge, this charge will repel it strongly in this direction. This charge will repel it strongly in this direction. Well, but not as strongly because it's further away. And when we add the two vectors, we get that the field line goes like this. Something worth noting, a field line shows the direction of the force on a positive test charge. It doesn't show the path that it would follow. Okay, so if I put a positive test charge, say right here, it's not going to necessarily follow this path. Got that? Okay. So what if we have unequal charges? Well, it might look something like this. These have different signs and different magnitudes. Which one is the positive test charge? That's right. This one is because positive charge, because it would repel a positive test charge. The arrows are moving away from it. This one is a negative charge because it would attract a positive test charge. Keep in mind that if we use a negative test charge, it will actually go in the opposite direction of the arrows. And sure enough, if I say pick a point in space out here and pretend I put a positive test charge there, we would have a force from this repelling it. We would have a force from this attracting it. And when we add those two forces together, arrowhead to endpoint, we would end up with a force right there pointing in, well, I'm trying to draw a tangent to the curve. I'm doing a terrible job there, pointing about in that direction. That make sense? So that's how you draw the electric field, and sometimes they can be very, very pretty. The electric field, then, is the electric force per unit of charge. That is, if you have a bigger amount of charge in the field, it'll experience a larger amount of force. Per means divided by, so it's a really simple definition. The electric field is the force experienced by a charge divided by the amount of charge. Again, remember, we don't necessarily know where the electric field comes from. We don't know what forces or what charges are causing it. This charge that I'm indicating right here is the charge that is feeling that force. So for example, if this is a negative charge, then the electric field and the force are in opposite directions. Got that? If it's a positive charge, then the electric field and the force are in the same direction. It's measured in newtons per coulomb because force is in newtons and charges in coulombs in the SI system. Q naught is the charge that feels the force. If you want to find the magnitude of the electric field around a charge that's causing that electric field to exist, the formula can look like this. This is basically Coulomb's law, except with the second charge divided out. Remember, electric field is force divided by charge. So if we take Coulomb's law, remember Coulomb's law, force is K Q1, Q2 over the distance between them squared. If we divide both sides by the second charge, that'll cancel it out. And so we get that the electric field, the force per unit charge, is just K times the charge causing it divided by R squared. It'll still be in newtons per coulomb, but it would have other units as well. Okay? All right, let's do some computations to make a little bit more sense of this. An anti-helium nucleus, what the heck is that? Well, remember, every particle has an antiparticle associated with it that has the same mass and other qualities, but it has the opposite charge. So an antiproton is like a proton. It has the same mass as a proton, but it has the opposite charge of a proton. An anti-electron, which is called a positron, by the way, has the same mass as an electron, but a positive charge. So an anti-helium nucleus would have two antineutrons and two antiprotons. It's in an E field of 4 newtons per coulomb that points down. What is the acceleration of the nucleus? Well, to compute acceleration, of course, we need force, we need mass. So here's our nucleus. Its charge is -2 times the charge on a proton. Remember, it's anti-helium. And its mass is about 4 times the mass of a nucleon, a proton or a neutron. It ends up being 6.64 times 10 to the minus 27th kilograms. Okay, so how do we compute the acceleration? Well, let's just look ahead here. We know that acceleration, let me change colors there. That's not so good. There, that's a little bit better. We know that acceleration is force divided by mass. That's Newton's second law of motion. Okay, so how do we find the force? Well, since we learned that the electric field is force per unit charge, then that means the force is really easy to compute. It's just the charge experiencing the electric field times the electric field. It's actually that simple, right? Isn't that easy? This is why we deal with electric fields. It makes stuff easier. And so that's going to be Q, which is -3.2 times 10 to the negative 19th power, times the electric field, which is, well, 4 newtons per coulomb. I probably should have written that over here. The electric field is 4 newtons per coulomb, and it has a direction, down. It is a vector. Vectors have direction. And so times 4. Notice this is in coulombs, this is in newtons per coulomb, so our answer is going to be in newtons, and it's going to be -12.8 times 10 to the minus 19th. Yeah, I know that's bad scientific notation. Just hold your horses there, okay? Newtons. But the question asked for acceleration. This is the force, the charge times the electric field. The acceleration, as noted, is the force divided by the mass. Let's just look at the magnitude of the acceleration first. Let's make that A look a little bit more like an A. And so we would have 12.8 times 10 to the negative 19th divided by the mass, which is 6.64 times 10 to the negative 27th. And we get an acceleration of, wait for it, is this going to be a big number? This is going to be a huge number. It's going to be about 1.9 times 10 to the 8th power meters per second squared. Wow, that's a lot of acceleration. It's going to not be able to maintain that very long or try going past the speed of light. That's a really big amount of acceleration, 190 million meters per second squared. So it's going to have a rapidly changing velocity if nothing stops it, and something will. You get the idea? Any questions? Okay, that's how easy it is to use the electric field to compute things. Let's try another example here. Suppose that a 5 times 10 to the negative 9th coulomb charge is at the point 0.02 meters, and a -3 times 10 to the negative 8th coulomb charge is at 3,0 meters. Find the strength and direction of the electric field at the origin. Well, I think a good idea, a nice way of dealing with this would be to start by kind of drawing a picture. So let's draw some axes. Okay. Hey, I actually drew a straight line. The point 0.2 might be about here, so we're going to put a charge right there. We'll call that Q1 is 5 times 10 to the negative 9th coulombs. And then at 3,0, 1, 2, 3, we'll put another charge right here, maybe call that Q2. And we want to find the strength and direction of the electric field at the origin. Now, I'm not going to go through all the computations here, but I'm going to lay it out for you here. Okay? The formula we're going to use is this. It's going to be that the magnitude of the electric field is going to be KQ over R squared. Okay? That's the formula. And we're going to use it twice because we have 2 charges to consider. Let's take a look at charge 1. What would it do to a positive test charge placed right there? Well, it's positive, positive, and positive repel. it would cause a force vector in the downward direction. How do we find the magnitude? We could call that E1, electric field vector, by using this formula. So, oh, what the heck? Let's go ahead and do it. E1 would be K. I'm going to call that 9 times 10 to the 9th. We're going to do some serious rounding here. Times the charge magnitude, which is 5 times 10 to the negative 9th, divided by the distance from this charge to the point where we're measuring the field. Well, that's 2 meters, 2 squared. And so that's going to be 9 times 5 is 45. The 10 to the 9th and 10 to the negative 9th cancel. Divided by 4, that's 11.25 newtons per coulomb. So this one right here, we already know is 11.25 newtons per coulomb, and it points down. Got that? But there's a second charge to consider. We need to consider what happens to this same positive test charge due to this negative charge right here. Well, that's right, it's going to be attracted, okay? I don't know what the strength of that is because I haven't computed it yet, but we would use this very same formula right here, except of course now we use Q2, and R is going to be different because it's now 3 units away, or 3 meters away from the origin. So this Q right here will be 3 times 10 to the negative 8th, and this R down here will be 3, which of course we have to square. And so we get a different magnitude. Then we use our rules of vectors to add these two vectors, and we get our final answer. Our final answer for the electric field is going to look like this, and that'll be the answer to the question. And so it'll have some magnitude, which we'll use the Pythagorean theorem to find, and some angle, which we can use some trigonometry to find. And you'll have the answer for the strength of the electric field and the direction of the electric field at the origin. Answers the question. Any questions? If so, go ahead and ask your physics teacher, because I can't really hear them. Good luck. Practice some problems. Bye.